There is a star in the sky that should not exist. Not in the sense that it is rare or unusual. In the sense that, according to everything we know about the age of the universe, it is mathematically impossible. The universe is 13.8 billion years old. We know this. We have measured it from multiple independent directions, from the cosmic microwave background, from the expansion rate of space, from the ages of the oldest known structures. 13.8 billion years. That number has been confirmed more times than almost any measurement in science. And yet, 190 light-years from Earth, in the constellation Libra, there is a star that our most careful observations suggest is older than that. Not slightly older. By some estimates, 16 billion years old, older than the universe that supposedly created it. Astronomers named it the Methuselah Star, and they have been trying to explain it ever since. The star was first catalogued in 1912 by American astronomer Walter Sidney Adams, who measured its radial velocity, the speed at which it moves toward or away from Earth, and noted that it was unusual. At the time, stellar ages were not something astronomers could calculate with any precision. For decades, HD 14283 was just a number in a catalog, a fast-moving star, notable mainly because it zips across the sky more quickly than most. It took most of the 20th century and the development of increasingly sophisticated computer models of stellar evolution before anyone realized what they were actually looking at. By the 1990s, astronomers had the tools to estimate stellar ages with real confidence. They looked at HD 14283, they ran the numbers, and the numbers came back wrong. The star appeared to be older than the universe itself. The measurement created a quiet crisis. Not the kind that makes headlines, the kind that gets discussed in hushed tones at conferences, filed in papers with careful hedging language, and quietly handed to the next generation of researchers as an unsolved problem, which is exactly where it stayed for years. To understand why this is a problem, and not just a measurement error to be quietly corrected, you need to understand how astronomers estimate the age of a star. Stars are not clocks. They do not have timestamps, but they do have something useful: chemistry. When the universe was young, it contained almost no elements heavier than hydrogen and helium. The periodic table beyond those two elements was essentially empty. The heavier elements, carbon, oxygen, iron, all the metals, were forged inside stars over billions of years and scattered across the cosmos when those stars exploded. This means that the chemical composition of a star is a record of when it formed. A star born early in the universe, before many generations of stellar explosions had scattered heavy elements into space, will contain almost no metals. Astronomers call these stars metal poor, and they use metal content as a rough calendar. The less iron a star contains relative to hydrogen, the earlier in cosmic history it likely formed. HD 14283 is extraordinarily metal poor. Its iron content is roughly 1/10,000th that of the Sun. By this measure, it formed very early, possibly among the first generation of stars to ignite after the Big Bang. The question has never been whether it is ancient. The question is whether it is too ancient. The most rigorous analysis of the Methuselah Star was published in 2013 by Howard Bond and colleagues at the Space Telescope Science Institute, using observations from the Hubble Space Telescope. They measured the star's distance with exceptional precision, a process called parallax, which uses the Earth's orbit around the Sun as a baseline to calculate how far away the star sits. Distance matters enormously for age calculations because it affects the star's luminosity, and luminosity connects directly to where it sits on the plot that describes a star's life cycle. The result, HD 20083, is 190.1 light-years away. Bond's team then combined this distance with the star's apparent brightness, chemical composition, and position on the stellar evolution track, and produced an age estimate of 14.46 billion years, plus or minus 800 million years. At the low end of that error range, the star is 13.66 billion years old, just barely consistent with a universe 13.8 billion years old. But only just, and the central estimate remains above the universe's age. That central estimate refuses to go away. Bond's paper was careful, exhaustive, and technically sophisticated. It acknowledged the tension directly. The star might be consistent with the universe's age within measurement uncertainty, but it might not be. What makes the Methuselah Star genuinely strange is not that a single measurement came back slightly too high. Measurement errors happen. What makes it strange is what the star does not contain. When the Big Bang produced the universe's first matter, it created hydrogen, helium, and tiny traces of lithium. Nothing else. The first stars that ignited in the darkness of the early universe were made of almost exactly that mix. When those stars died, either collapsing into black holes or exploding as supernovae, they seeded the universe with the first generation of heavier elements. The stars that formed from those seeded clouds were slightly less pure, slightly more metal-rich, and so on through billions of years of stellar generations, each one carrying a faint chemical fingerprint of when it was born. HD Q283 sits at the very beginning of that chain. Its chemistry is consistent with having formed from the very first enriched gas clouds, material that was mixed with the ejecta of the earliest supernovae in the universe's history. This is not a star that snuck in from somewhere unexpected. This is a star that appears to have formed in the universe's first window of star-forming activity. The problem is that first window, by our best calculations, opened roughly 200 million years after the Big Bang, which puts the star's birth at about 13.6 billion years ago. And the universe's age at 13.8 billion years. The margin is almost non-existent. There are three ways to resolve the Methuselah paradox, and astronomers have explored all of them. The first is that our measurement of the universe's age is wrong. The age of the universe is calculated primarily from the Hubble constant, a number describing the expansion rate of space. This number has been measured by different teams using different methods, and for years those methods have produced slightly different answers. The discrepancy is small but real, and it is called the Hubble tension. Some physicists have argued that the Hubble tension points to new physics, unknown factors that have affected the expansion of space in ways our current models do not account for. If the universe is actually older than 13.8 billion years, the Methuselah star fits neatly within it. The second possibility is that our age estimate of the star itself is slightly too high. Stellar age calculations depend on models of nuclear physics inside stars, and those models, though highly refined, contain assumptions that could introduce errors. A slightly different value for the rate at which hydrogen fuses inside a very old, metal-poor star could push the age estimate down by hundreds of millions of years, enough to resolve the conflict. The third possibility is stranger. Some theorists have proposed that the star could have received a burst of fresh hydrogen from a merger with another object or from drifting through a particularly dense region of interstellar gas that effectively reset some of its internal clock, creating an illusion that it is older than it actually is. None of these explanations has been confirmed. All three are actively debated. What the Methuselah star has become over decades of study is something more important than a single anomaly. It has become a stress test for cosmology. Every time a new measurement of the Hubble constant comes in, astronomers check it against the star's age. Every time a new model of stellar physics is published, someone runs it against HD 410-283 to see whether the tension shrinks. The star is a calibration point, a fixed object that forces every cosmological model to prove it